Die Sprachübertragung beginnt jetzt. Alle Teilnehmer befinden sich im Zuhörermodus.
Good afternoon and welcome to our webinar on external reference standards or relative response factors. Some considerations here for the quantitation of impurities in pharmaceuticals. My name is Christian Seine, and I am the Global Product Manager for our pharmaceutical reference standards at LGC. And I am very happy to get this presentation being done by Dr. Bernhard Olsen, who is supporting us on webinars, on white papers, and he will also refer later to a white paper that we have set up on the topic. I will also introduce Bernhard in a few minutes, but before we come to that, I would like to show you a few things. First of all, you can see here, I hope on the screen now, the panel with which you can put questions in to us. There's a question field there where you can put your question in, and we can answer the questions later at the end of the webinar. There's also a hand raising button, and let's see if that is working. If you can hear me and can see the screen, please can you click on the hand raising button, and we can see if it is all working here correctly. So yes, I see people raising their hands, so it seems to work here very well. Okay, then with that said, let's go to the next slide, and I would like to introduce Mikromol, our brand for pharmaceutical reference standards, to you. Most of you have heard probably already about our line of over 5,000 impurity reference standards or reference standards for active pharmaceutical ingredient and excipients. We have that available for more than 1,000 API families. And they are suitable materials for qualitative and quantitative applications in method development, in validation, and in routine quality control. For API testing, for excipient testing, but also, of course, for finished dosage form testing there as well. And our materials come with an extensive certificate of analysis. We have very comprehensive, detailed certificates for impurity reference standards, and we also provide even more detailed certificates of analysis for our API reference standards that we have produced under the ISO guide 17034, or I should say ISO standard 17034. We can also provide expert technical support and advice on technical applications for pharmacopoeial methods and also internally developed protocols. And yeah, with that, I would give the word to Dr. Bernhard Olsen. Let me please introduce Bernhard to you. So Bernhard is a PhD, is a doctor, and received his undergraduate degree from the Nebraska Wesleyan University in chemistry and his doctorate in analytical chemistry from the University then of Wisconsin-Madison. He is an independent consultant providing expertise in chemistry, manufacturing, and control to the pharmaceutical industry. He has over 37 years of experience in drug development, including 29 years at Eli Lilly, where he was a senior research fellow and contributed to the development and support of over 25 commercial drugs and numerous developmental drugs. He has published and given invited lectures on a wide array of drug development and analytical topics, including high-performance liquid chromatography, method development and validation, impurity determination and control, genotoxic impurities, physical property characterization, drug counterfeiting, regulatory aspects of drug development, and quality control. And Bernhard is also a fellow of the American Association of Pharmaceutical Scientists. And with that, Bernhard, I give you the floor and hand over to you.
Okay, thank you very much, Christian, for that kind introduction, and to LGC for the opportunity to speak this afternoon about external reference standards or relative response factors. This is a topic and decision that often comes up in the determination of impurities in pharmaceuticals. So it is fairly common to encounter this. We know that from a regulatory standpoint, as given in ICH Q3A guidelines, that you can measure impurities by a number of techniques, and often this is done by comparing an analytical response for the impurity to that of a reference standard of that impurity, or it is also acceptable to compare to the reference or the response of the drug substance itself. And if you're using the drug substance as a standard, then it is appropriate, especially when the responses differ for the impurity and the drug substance, to use a correction factor to make sure that the impurities are being accurately quantified, or if there's going to be an error made, that they're being overestimated, because that is would be on the safe side to overestimate. So one thing right off the bat to define is how relative response factors are expressed. And when throughout the talk, when I'm talking about RRFs, I'm referring to them as defined here, where it's really the response factor of the impurity divided by that of the API. So the response factor being whatever detector response is being measured, divided by the impurity concentration. And it's important to realize that this is expressed differently in the in USP and European pharmacopoeias. USP, usually a factor F is used in calculations, and it's equivalent to the RRF as I've described here. And it appears in the denominator of calculations, so you're usually dividing by that. Whereas in the European pharmacopoeia, it's often listed as a correction factor, and the value would be the reciprocal of the relative response factor, and it appears as a multiplier in the numerator. So the message here is to be sure you know how the number is being expressed and how it's being used in impurity calculations. So how does one go about determining a relative response factor? I think a very common way of doing this is by comparing the slopes of linearity plots for the API and compared to the impurity. So here we have the detector response versus the concentration of the compounds of interest. And just as hypotheticals, here's the slope for the plot for the API, and the relative response factor then would be simply the slope of the impurity plot divided by the slope of the linearity for the API. So in this example, impurity 1 would have a relative response factor greater than 1 because it has a greater slope, while impurity 2, the value, RRF value, would be less than 1. And you note here that I've made a notation about the compound concentration, and the point there is that to have an accurate RRF determination, the concentration of both the API and the impurity solutions must be known accurately. So usually for the API, this is done with the API reference standard where you do know that accurately. But there can be questions depending on how you go about calculating the concentration of the impurity solutions. So we'll be discussing that in a minute. Before doing that, however, I think it's fair to say that the most accurate and robust way to quantify an impurity is to use the a standard, external standard of that impurity itself. But there can be cases where that's maybe not as desirable, or some difficulties in doing that. And then a relative response factor may be appropriate. In one case, it may be quite difficult to isolate or synthesize an impurity in sufficient quantities for routine use. However, kind of as indicated in Christian's one opening slide, there has been an increase in the availability and perhaps decrease in cost of obtaining some of these standards over the years. So that's a consideration. Standards have to be characterized in order to be used accurately. And the thing to note here is that in order to determine an RRF, this is necessary as well as if you were doing it with the impurity standard itself, doing the external standard quantitation. So it's actually best to use a characterized standard for the RRF determination, even if you're not going to use it routinely. Another motivation for using RRFs instead of external standards can be laboratory efficiency. Some labs don't want to prepare a number of external standard solutions, and use of RRFs may help with that in some cases. When we have complex impurity profiles, this may cause some difficulty in using standards for all of the impurities that may be present. And here I think it's important to give priority to the specified impurities. In other words, those that are being reported individually may get more consideration for using an external standard rather than an RRF compared to some of the other impurities that may be present. So with that, back to how can we avoid errors in the RRF determination caused by errors in the in what we assign as the sample assay of the impurity. And this can happen when components of the impurity sample or standard, if you will, are not accounted for in the determining the concentration. And some common examples are if the impurity is present as a salt and that has not been taken into account. Also, the moisture levels present, residual solvent levels that may be present, or other impurities that might be there need to be considered. And I just showed this typical assay calculation based on mass balance that is often used to assign an assay to a reference standard, where you start with 100% and subtract the other things that are present. So the moisture and the residual solvents, and in this case, the corrected by the area percent purity, usually determined by HPLC. And clearly here the salt form has not been accounted for, but that would have to be taken into account as well. And an interesting example of kind of inaccuracies that can be encountered will be shown here, where we have this compound chlorophenylpiperazine hydrochloride. And we know from the literature that when present as the free base, it's a liquid with this molecular mass. And it can also be present as the hydrochloride salt with the corresponding molecular mass, a Cass number, and in this case it's a solid with a melting point around 212 or so. But this is dibasic, so it can be also presented as the dihydrochloride salt that's known with a different Cass number, and the melting point here is actually around 190. And if you do the calculations based on the free base amount of the organic moiety here, you see that it makes a difference what salt form you have when you're using this to determine a relative response factor. And as it turns out, this compound is available from several commercial sources, and LGC did some investigating here and found that from one supplier in the catalog, the mass was listed as the free base mass. The Cass number, however, was listed as the hydrochloride salt as well as the melting point. But when actually furnished, the material turned out to be the dihydrochloride salt. So that could present an issue. Supplier 2, in this case, listed the hydrochloride mass and Cass number and melting point, but when received, the material was the dihydrochloride salt. So again, some confusion could result if one did not characterize this well. And then to add to the confusion, supplier 3, in this case, had the hydrochloride mass, the dihydrochloride Cass number, and melting point, but in fact, in this case, it was the hydrochloride salt that was received. So you can see that some caution is necessary, and if you don't get a characterized material, you will have to do some level of characterization to know its assay accurately. Another consideration for use of relative response factors instead of external standards is potential robustness issues with those. And by that I mean, is the RRF going to be constant from run to run? And this was a case that I encountered where I showed the spectra for, here in blue, the API, and two impurities, impurity B that has a spectrum shown in green, very similar to that of the API. However, impurity C, the spectrum, the maximum was shifted quite a bit, and normally one might want to do detection out here at 305 or so at the API maximum, but impurity C would be invisible there. So it turns out we looked at going to 280 nanometers for detection of where we could see both impurity C and B, and those could be quantified versus A with the use of a relative response factor. However, and you may be anticipating the issue here, but the issue with that is that the RRF for impurity C will change by about 30% with a small wavelength change, as little as plus or minus 2 nanometers from the nominal 280 nanometer wavelength. And when you look at the spectra here, that may maybe not be too surprising. We're on a very steeply sloping portion of the impurity C spectrum, and even bigger. Well, to compound that problem with small wavelength changes, the slope of the API spectrum is in the opposite direction. So one response goes up. If we go to lower wavelengths, the response for C goes up while the response for the API goes down. And so that leads to this quite large discrepancy in RRF value with even a small change in wavelength. If you look at impurity B, however, its relative response is going to remain virtually constant, even with large changes, because the spectra are so similar. So, at least in my experience, these things are not often investigated carefully during development and validation of a method, and can lead to problems, especially day to day or instrument to instrument, lab to lab, those sorts of things. Other robustness issues that one should consider is whether the detector bandwidth might cause some problems with the consistency of an RRF, or whether it makes a difference whether you're using a variable wavelength versus a diode array type of UV detector. So having said that about robustness, back to determination of RRFs, and a question that's often encountered is, can I use a qualitative impurity standard or sample, often something from a research lab or research catalog, to determine an RRF? And basically the answer is you can, but you need to think twice about how you're going about doing this, because there can be an impact. For example, if you obtain a sample of an impurity and it's indicated as, well, this is greater than 80% pure or assay, or something along those lines, then the question becomes, well, what value should I use to determine or calculate the concentration that I'm using to determine the RRF? Should it be 80%, 90, 100%? Really no idea about this. And in previous webinars, LGC has found that when the audience is polled, there will be numbers across all these choices, including a fair number of folks that will say, I really don't know. And it's often a minority that will give the what I would consider the correct answer. And that would be to not calculate with the minimum value of 80%. And why is that? Well, one is that the material is probably purer than that, and that would risk overestimating the relative response factor. And we'll see that when you overestimate the RRF, that would lead to underestimating the impurity quantitative result. and we don't want to do that because that's more of a safety risk. And so, if anything, we want to err on the safe side and assume that the material is 100%. And this then has the risk of underestimating the relative response factor. And just to keep in mind that when we overestimate, as I mentioned previously, the RRF, that causes the impurity content to be underestimated because you're dividing, remember this is in the denominator, by a larger number. And conversely, if you underestimate, this causes an overestimation of the impurity content. So what about overestimating the impurity content or impurity level in the sample? What can be the consequences of that? Well, from a regulatory standpoint, as we said, the error would be on the safe side. You would fail something and not use a material. And so even if it was not really out of spec, you would err on the safe side and patients wouldn't be exposed to unsafe levels. However, that does definitely present an economic risk for pharmaceutical manufacturers. And that's because either a false positive OOS that results in unnecessary investigations or rejection of material, or during development, if you if you're overestimating an impurity, it could lead to exceeding the impurity qualification threshold, which could lead to unnecessary, time-consuming and expensive qualification studies. So something to indeed watch out for. We've looked at that even further to see, how likely is that, and prepared this little graph where we've plotted the percent error in impurity quantitation, assuming 100% assay of the impurity reference standard that is used to determine the RRF. And this would apply for actually for direct determination using an external standard. If you had to assume 100%, you didn't know the true assay. So clearly, if the true value is 100%, there is no error associated with that. If we go to a somewhat extreme case and the true assay is only 50%, then really the error in assuming that it's 100%, the error becomes 100%. Because you're off by that amount, assuming that level. And just to take an example of somewhat of a midpoint, if you go to 70%, now you're still at an error of 43% in impurity quantitation. And that would mean that if an impurity was actually present at 0.12%, this level of error would, again, it's on the safe side, but you would report the value as 0.17%. And now you've, in development anyway, exceeded the qualification limit of 0.15%, which could lead to the need for toxicity studies that would in fact not actually be necessary. So other considerations for RRFs. Is there a limit to the range where we should use these? And one recommendation is given in the EDQM guide for elaboration of monographs, where It's recommended to not use RRF values below 0.2. And actually in the guide, it's listed as the correction factor, which is 5, because they're inverse of each other. And you can think about why that makes sense, because now you're really going to magnify any errors or variability in the quantitative results from the analysis that are caused by integration variability or chromatographic baseline issues. And now you'll be, in effect, multiplying those by a factor of 5. So in cases like that where the response is quite low for the compound compared to the API, it's better to use an external standard of the impurity, or to go to a different wavelength where the response factors might be more similar. Another thing that has shown up in the past is the impact of an RRF that was inaccurate to begin with on the product life cycle. We know that even after approval, there can be efforts to improve methods, either for robustness, efficiency, accuracy sometimes. And that when you go to compare results with new or revised methods with the old method that incorporated an inaccurate RRF, that they may or may not be comparable. This can also carry over into specifications if these have been set based on inappropriate or inaccurate relative response factors. So that's another important thing to consider. So to summarize in conclusion, I think most would agree that the best case for impurity quantitation for accuracy and robustness would be to use a reference standard of the impurity itself that has been well characterized, but that in some cases RRFs can also be used with success, but they should also be defined accurately using a characterized sample or standard of the impurity. Potential ruggedness issues should be considered and investigated to avoid problems with continued use, especially transferring to other facilities and so forth. And that if anything, we want to err on the side of having a overestimation, but realizing that this is going to incur potential economic risks, but wanting to avoid the safety risks of underestimating impurities. And that inaccurate RRFs also will cause difficulty, or can cause difficulty in comparison of results between methods. So with that, I would again like to thank LGC for the opportunity to speak this afternoon. And as Christian mentioned, much of this content is given in a white paper that can be accessed through this link. And I believe the link will be sent out to the attendees in a follow-up email. I would also like to acknowledge and thank the LGC scientists who furnished the slide on the interesting examples of different salt forms that can be obtained with sometimes without knowing it. And of course, to those attendees for your attention. I think we have some time for questions, and I believe Christian is also willing to take questions later via email if you want to wait. But I think you can send some now through the chat feature. And with that, I'll turn it back to Christian.